Welcome back to this SIPROTEC Process Bus top-level qualification training. My name is Yelitza Rojas, and today we will talk about the network architectures for the Process Bus stations. We will see some examples, and to start, then let's consider the technical principles that we saw in the last chapter. All of them need to be taken into account during our design phase. The first one, the sample value synchronization, which we can achieve using either the PPS signal or the precision time protocol. The communication reliability, which can be done with the PRP protocol or with the HSR. And the interoperability that would be granted with the edition 2.1 of the IC 61850 standard, and using either the light edition or the flexible streams. So let's start talking about the influence of the type of the stream in our network. And we can do it with an example. So here we have one substation in a circuit breaker and a half configuration, and we take the upper diameter where we need to transmit 8 different currents and 4 voltages. For that, we have installed one measuring unit, and let's see what we need if we want to use light edition streams. So we will need to pack 2 different streams, one with the information of the first current transformer and the voltage transformer, and a second stream for the second current transformer, and we will also need to pack a voltage transformer. If we don't have it, as in this case, then we will be using 0 signals, but nevertheless 8 values in the stream. If instead of that we use a flexible stream, then we can pack all the information, the 8 currents and 4 voltages, in one single stream. And that means if we use the 4800 Hz sampling rate with light edition and the 2 streams, we use almost 13 megabits per second of the bandwidth. But if we use the flexible stream, then we reduce this to less than 8 megabits per second, which means almost a 40% of reduction. That's why our recommendation is using the flexible streams to take advantage of the complete bandwidth in your process bus network. Here you have a couple of tables that can help you to know the use that you are doing in your network depending on the type of the stream and also the different sampling rates that can be used. Normally, in the backbone, we will have a lot of information. So we will have gigabit networks there, but in the protection devices, it is enough having interfaces with 100 megabits per second. For reducing the amount of information coming into the protection devices, we can use different methods. We can use the multicast filtering in the switches. We can use the segmentations with virtual LANs or VLANs, or we can also implement a physical network segregation. Other important topic is the ASDU. You can also optimize the use of the network when you pack more than one in the same stream. Nevertheless, you have to take into account the more AS2 SDU that you have in the same stream, the more values that you lose in case one stream gets lost. So your protection device should be able to interpolate all those values to keep the protection system running and operative as required. As a design value, keep the use of the network below the 60% 4 sample measure values. In such a way, you can be sure that all other messages, as goose messages or synchronization messages, can also be transmitted without any risk of overflow. So now let's see some architecture examples. We saw that depending on the type of synchronization, so we can use the PPS or we can use the PTP. If we want to go for the PPS synchronization, mainly if you have already existing stations or if your application is really small, and then for that we will use one communication interface, one serial one, or we can also use the G port of the devices. Keep into account this G port receives an electrical signal, and therefore the source of the PPS should be close to the device. So let's start with the first example, where we have one HSR ring and we use the PPS for the synchronization. So here it's clear that we need 2 different networks to distribute the 2 types of information. Through the blue line, we will see our sample measure values being transmitted, and through the red line then we will see the pulse per second. For this we have external devices. We need a GPS and also the so-called star couplers to distribute the different signals to the devices. Keep in mind that all devices should be connected to the same level of the star couplers. In this case, for example, if you have only 2 devices, you could connect these 2 devices directly to the 2 outputs of the master clock. But if you need more than 2, and in this case this GPS is only having 2 outputs, then you need to add star couplers to cover all the devices on the same level. With the SIPROTEC 5 devices from the version A60, this PPL signal can also be generated by the protection device. Keep in mind that this signal is not globally synchronized, but for the process bus is not relevant to have a synchronized, globally synchronized signal. What we need for the technology is having all the devices synchronized to the same pulse. In this example, the transformer protection is sending the PPS signal to the 2 merging units connected or required for the algorithm. So we have the output of the protection device connected to the first merging unit. This signal is mirrored and connected to the second merging unit. In this case, also the distance protection is generating the PPS pulse for its own merging unit. In this implementation, then you don't need to use external synchronization devices. Now let's see the example with HSR, but now using the PTP or precision time protocol. What we see here is always we have our redundant master clocks. We connect them also in a redundant manner from one GPS to the PRP-A and the PRP-B. Those are the backbone switches, and our ring is connected to this backbone to receive the synchronization signal. If we need only one ring, then we connect this output from the master clocks directly to the red boxes. This configuration that we have here is already prepared to receive additional rings. So all other rings will be connected to the different available ports for the PRP-A and PRP-B networks. We can also have then PRP networks using the precision time protocol. So here we have for the process bus our two networks, PRP-A and PRP-B, and our master clocks redundant and also connected in a redundant manner to both networks. This configuration is important because in such a way we grant that the master clocks are seeing each other all the time and they can define by themselves who is the one giving the synchronization signal, meaning who is the one acting as the grand master clock in the network. Here we are also adding an independent station bus. So the protection devices are connected on one side to the station bus and on the other side to the process bus. And with this configuration, we can also take advantage of the possible NTP signals that we have in the master clock to fit into the station bus for other devices like printers or PCs not able of receiving PTP synchronization signals. For PTP, the SIPROTEC 5 devices are supporting two profiles: the power utility profile according to the IC 61850-9-3 and also the power profile, the version from 2017. These two profiles can also be made available as interoperable. Just keep in mind that you need to give the right settings. So now let's see a little bit more complex network. This was taken from our process bus manual. And this is the configuration that you will use when you have substations with a higher amount of devices. So you will have to use different switches, and the way to connect them is using RSTP rings. So keep in mind that this configuration is a PRP configuration. So if you see, every device is connected to the red network, which is the PRP-B, and also to the green network, which is the PRP-A. So only the backbone switches are being connected with this RSTP ring. If you see, also the master clocks are double connected or connected as redundant attached nodes, once to the red network and once to the green network as well. If we extend this configuration with a station bus, then you see here the device is also connected to this black network. The station bus is completely independent. It can be RSTP, HSR, or PRP, depending on the need of the project. And here we are also using the same master clocks to feed NTP signals into the station bus. So here we can also see the primary part. So how can we get this redundancy, complete redundancy in the system? So basically, we will be having redundant merging units. So for process bus stations, we don't need to have 3, 4, or 5 different cores in the instrument transformers. It is enough having 2 and feeding one to the merging unit 1 and the second one to the merging unit 2, sending these 2 signals to the process bus network, where all the protection devices can access both type of information and select the one that they need for the protection algorithm. In this case, for the transformer protection, if you, for example, use transformer protection as main and backup, then the recommendation is having also redundant merging units on the low voltage side of the transformer. If you use as main protection the transformer protection, but as backup only an overcurrent, then you will need only one merging unit in the medium voltage part. We are also showing here the separated station bus, and this is basically the diagram or the schematic from a complete digital IC 6150 station. So now, to take away, the three key aspects of the technology shall be considered during the design phase, which are seamless redundancy, the sample value synchronization, and also the interoperability. The type of stream that you use will impact the use of the bandwidth in the network. That's why we recommend using flexible streams. A maximum of 60% of occupation of the bandwidth using sample measure values should be considered, so you have enough bandwidth for other type of information as ghost messages and synchronization messages as well. And the traffic in the network can be controlled using multicast filtering in the switches, virtual LAN separation, or physical segregation in the network. So this is the end of our second chapter related to the different type of architectures that we can use in our communication network. Thank you for joining us, and see you soon.